What is calculating stress in engineering design? Imagine holding a heavy box in your hands. Your hands feel the weight, but inside the box, tiny forces are pushing and pulling on the material. That's what engineers need to understand when designing strong, safe structures. Calculating stress is the process of figuring out how much internal force is acting on a specific part of a material when external loads are applied. It's like measuring how much a bridge or a building's component is being squeezed, pulled, or twisted under real-world conditions. The basic idea is simple. You take the force applied to an object and divide it by the area over which that force acts. This gives you the stress, which is measured in units called pounds per square inch or newtons per square meter. For example, if you push down on a steel rod with 100 pounds of force and the cross-sectional area of the rod is 1 square inch, the stress is 100 pounds per square inch. This calculation assumes the force is perpendicular to the surface, which is common in many cases like pushing or pulling. There are different types of stress depending on how the force is applied. Tensile stress happens when you pull or stretch a material. Compressive stress occurs when you push or squeeze it. Shear stress is when forces act parallel to the surface, causing layers to slide past each other. Other types include bending stress, which happens when a beam is bent, and torsion, which is twisting. Each type affects the material differently and can lead to failure if the stress exceeds what the material can handle. Calculating stress is key to predicting when a material might fail. If the stress inside a part becomes higher than its strength, it can deform permanently or break. Engineers use these calculations to make sure the stress stays below safe limits, often adding a safety factor. This safety margin accounts for uncertainties like unexpected loads, material flaws, or wear and tear over time. More advanced analysis involves understanding how stress varies within a structure. For example, in a beam, the stress isn't the same everywhere. Some points experience higher stress than others, especially at corners or where loads are applied. Engineers use tools like Mohr's circle to visualize different stress states and find the principal stresses, which are the maximum and minimum stresses at a point. This helps identify the most vulnerable spots that might crack or fail first. In real-world design, calculating stress helps engineers create products and structures that can support their intended loads without breaking or deforming. If the calculations are off or safety factors are too small, the material might crack, bend, or fatigue over time. That's why understanding and accurately calculating stress is so important. It helps explain why some mechanical parts break unexpectedly and guides us in designing safer, more reliable machines and buildings.